All right, so I just wanted to take a little bit of time to talk about conservation of energy, talk about how it relates to work, and why we might want to use conservation of energy instead of the work energy theorem. So up until now, we've really been relying on this equation, right? So we've been thinking about how the change in kinetic energy of an object is related to the work done on the object, right? So this would be the work done on an object, and that reflects how much the kinetic energy changes by. Right, so if we just take a simple system, for example, like a pendulum, right? Let's say this thing swings down, and at the lowest point, this pendulum bob, it's not an awesome drawing, but at the lowest point, that pendulum bob would have some kinetic energy. Right, so one way of thinking about this is that work done by gravity on the object is transformed into kinetic energy. Right, so gravity does work and gives the object kinetic energy. And this is a valid way of thinking, right? Because gravity is the only force that's going to do any work on that object. But this is only one way of thinking about the problem. So the way that we're thinking about it right now, we're really just considering this sort of object, the pendulum bob, as a system. And that is not a closed system, right? Because gravity is an external force, right? Gravity comes from the Earth. That's an external force that's giving energy to this system that consists of just the pendulum bob. But another way we could think about it is we could consider the system of the pendulum bob and the Earth. Right, so if we consider the pendulum bob as well as the Earth together, right, these two together are a closed system, right? Earth plus pendulum is a closed system because that gravitational force on the pendulum bob, right, that's coming from the Earth. So if we think of this whole thing as a system, then that is not an external force. And the increase in energy of the pendulum, we can think of that as just a change in energy of this system, right? The pendulum Earth system. Rather than, in this case, right, when we were thinking of just the pendulum bob itself, right, when we were thinking of just that as the system, then gravity is an external force, and it's giving energy into the pendulum bob system. But if we think of this whole thing as our system, right, if we think of this whole thing as our system, then that gravitational force is internal, and instead of the Earth sort of putting energy into the system, really we just have a transfer of energy from potential energy of this system into kinetic energy. So if we think of it as a closed system, we can, instead of thinking in terms of work, we can think in terms of energy transforming. Right, so the initial energy of our system is equal to the final energy of our system. And just initially, we start with only, right, if we think about the types of energy, there's gravitational, kinetic, these are initial, and then, right, we have some final energy. And in this case, we could say something like, okay, well, there's no initial kinetic energy, there's no final potential energy. So that potential energy that this pendulum bob initially had by being at, some height above that point, right? That potential energy is converted into kinetic energy. So the pendulum Earth system has a transformation in what type of energy it possesses, right? We have a change of energy from potential to kinetic, but we don't have any outside work being done on this system. So both of these ways of thinking, you'll be able to calculate the final velocity or final kinetic energy of that pendulum bob, but they're just sort of two different ways of conceptualizing of it, right? One of them is by thinking of the force as kind of an external thing, doing work on the pendulum, giving it kinetic energy. But if we think of the pendulum Earth system together, we can think of this kinetic energy rather as just a product of a transformation of one type of energy to another within that pendulum Earth system. Okay, so a little bit, maybe a few different kind of examples for how to set up something using conservation of energy. So there's really two different ways to do this. One way is to just do, let's say, take the initial energy of the system and put this equal to the final energy of the system. So let's say, for instance, that we have a block and that block is dropped a height, let's say some known height, let's say h, right? So this height is h. And we want to figure out, well, how fast is it going when it hits the ground? So one way to think of this would be to think of the initial and final energy of the block Earth system and relate them to each other. So we could set this up. We could say the initial energy is going to be the sum of kinetic and potential energies. So the initial energy is U gravitational initial plus K initial, and the final energy is U gravitational final plus K final. Initially, we have no kinetic energy, so this is 0. And I'm going to go ahead and say that the ground level is our height of 0. And we're going to see in a minute that you could actually change this, and everything will still work out. But let's just keep going. So what that means is this final gravitational energy of the block will be 0, right? So we're comparing the energy of the system at 2 times. One time is when the block is here. That's our initial time. And our final time is when the block hits the ground. So that's what this, or right before the block hits the ground. That's what this portion of the equation represents. So the initial gravitational energy would be equal to mg times the initial height, which is just h. Let's just say this has mass m. And then the final kinetic energy would be 1/2 m times the final speed squared. And then we end up with this equation 2gh equals v. So if we square root that, right, we get v. Notice that it doesn't matter what path it takes. So this relates a little bit to our discussion we had the other day when we were talking about sliding a block down a weird path. Right? If this went down a slide to the ground, we would actually get the same result here, because the only thing that matters is the change in height. It doesn't matter how it gets down, so long as there's no friction. Okay, so what I'd like to do now is I would like to solve the same problem, but I want to see what, because there's nothing special about the ground, right? So I decided to call the ground my sort of height 0 in order to measure gravitational potential energy above. But you can actually set any vertical position to be our height of 0, and we end up with the same result. So what that would look like, let's just take this exact same exact same thing. Let's put it down here. But now what I'm going to do is I am going to make, let's say, this my h equals 0. All right, so right in the middle. Maybe I shouldn't use h. How about I'll use y to represent that. So if I go to set up my equation, right, E initial equals E final, right, and these E's represent the total mechanical energy of the system. Then I plug in, this is UGI plus KI equals UG final plus K final. Now here, since I made this sort of middle height my 0, the initial height is actually, if this length is h, this is h over 2. And this is also a distance of h over 2. Right, and we have to call up the positive direction for gravitational potential energy. So up is positive. This is basically my origin. Whereas here, right, this was my origin, and this way was still positive y. Okay, so now if I go to plug stuff in, my initial gravitational potential energy is actually mgh over 2. And my initial kinetic energy is still 0 because it starts from rest. My final gravitational potential energy is actually going to be negative because I'm below the origin. It's a little bit weird. So my final gravitational potential energy is actually negative mg h over 2. And then plus final kinetic energy. So if we look at what happens, first m's cancel out, so I can throw that away. And then we get 1/2 gh equals negative 1/2 gh plus 1/2 v squared. I know I could throw away the halves, but before I do that, I'm going to go ahead and add this term to the left side. And if I do that, I get gh equals 1/2 v squared. And notice that this is the same thing I got above. Right? It turns out that it doesn't matter where I set that y equals 0. We end up with the same result for v. And this is really important because it demonstrates that gravitational potential energy, the actual value of it is totally arbitrary. You can choose whatever point that you want to set as your sort of y equals 0 when you're calculating gravitational potential energy, so long as you're consistent. Because the only thing that actually matters is how much the gravitational potential energy changes by. Right? It doesn't matter what the exact value is, it just matters how much it changes by, and you'll get the same answer. Okay, I want to do this again, but I'm going to give you yet another way of setting up these problems. So I'm going to go ahead and copy this one more time. And this is actually my favorite way to approach these. So another way we could set it up is we could actually do something like this. We could say the change in kinetic energy of the system is equal to the negative change in potential energy of the system. Right, so this, it looks different than this equation, but it's actually the same thing, right? So this basically says that if the potential energy changes by some amount, the total kinetic energy has to change by the same amount, but in the other direction, right? So if the potential energy increases, right, if delta U is positive, if there's a gain in potential energy, that means the system had to lose kinetic energy, and vice versa. So you could kind of set this up however you want. But if we come back to this question here, and really I do like this way of solving these problems, because if you solve it this way, you don't actually have to choose where you're calling a height of 0 if you set it up this way. So if we just look at these deltas, right, the change in kinetic energy is just K final minus K initial. Maybe I'll pull this down to clean up a little bit. Negative delta U is delta mg. Actually, we should put the delta on the y. Mg delta y. Now, the only part here is we have to be careful about our delta y. So in this case, delta y is negative, right? It's losing height as it goes down. So this delta y would have to be a negative value, right? Because y final is 0 and y initial is h. So if we plug that in, we get and I guess we can throw away this initial kinetic energy. But right there where we have delta y, that delta y is actually going to be equal to y final, which is 0 minus h. Right, we're literally taking our change in position. And I suppose I don't really need to have that bracket right there. So now if we actually solve this out, we get kf equals, the negatives actually cancel out with each other, mgh, and my k is just 1/2 mv squared equals mgh. And then again, we wind up with this same answer. right? So there's a lot of different ways you can kind of conceptualize of doing this, right? You can set up initial and final energies equal to each other, and if you do it that way, you can choose wherever you want to be your starting point, right? We saw that the where you measure the gravitational potential energy from is actually arbitrary because you wind up with the same result in terms of the speed of the object no matter what. But you can also set it up like this, right? Looking at how the change in kinetic energy relates to the change in potential energy of an object. So I hope this video was helpful. I hope I didn't add confusion in an attempt to add clarity. But really there were two things. One of them was to kind of explain why there are two different ways, or that there are two different ways of thinking about energy. One of them is to think about how if you take a single object, the work done on that object can affect its kinetic energy. But if you look at that object as part of a system, you can instead think about energy as just changing forms within that system. So, right, both of these are the same, really the same thing is happening, but depending on what you define to be your system, you can think about it in different ways. So I hope this was helpful. Let me know if you have questions, and keep up the great work, guys.